Okay, welcome back everybody. Today I'd like to finish up the bootstrapping example we've been looking at. Bootstrapping is a pretty simple idea. Instead of going back out into the population and collecting more data, you end up just resampling from your original sample. Now that's not going to give you a better estimate, point estimator. We'll look at that just in a second, try to convince ourselves that that's true, but it helps us to understand uncertainty. So by shuffling that data and resampling from it, you're getting different estimators and trying to understand the uncertainty. Let me just ask you a question. Does it over or underestimate uncertainty to Bootstrap?
Underestimate?
Yeah, I tend to think it underestimates, but it's possible. It's conceivable, just not likely that it could overestimate. Like you could kind of imagine that maybe you ended up getting a few samples from the tails, you know, in just a couple little samples. So if you just sampled a couple times and you just happen to be in the tails, it's really unlikely that that would happen, but it is possible. And then if you resample over that, your uncertainty's all coming from the tails, which is overestimating it. But David's right. Usually you're underestimating and you're not seeing things in the tails because they're unlikely. So you have a hard time of learning about extrema. So things like that. Bootstrapping wouldn't work well with trying to estimate the maximum in our uniform example, because we'd never see a sample over to the right of our maximum. But it kind of tells us maybe about the left-hand side, but since we're interested in the right-hand side, it doesn't really help us there. So there are some limiting cases. Let's just remember our example that we are looking at. We're going to be computing x bar. I'll just write it like this. Sum of the xi's divided by n. That might be our test statistic. Now this would be a silly test statistic to actually bootstrap over. It would tell us that we didn't know any math, because maybe we have the central limit theorem, and we're inclined to think for a reasonable sample that's normally distributed. So this is just an idea to compel us that bootstrapping might be a good idea. It seems to be doing approximately the right thing. But you could do this for more complicated statistics where you just didn't know what their distribution is. So in probability class, they're trying to show you what various statistics are. They focus a lot on this one and show you what their asymptotic distributions are. So if n gets big, how is this approximately distributed? So we know a lot about x bar right here. If we ended up bootstrapping, we come up with all these different replicates. So our original sample is just x1 to xn, and by sampling with replacement, we're going to come up with these different auxiliary data sets. So I can come up with an x. I'm going to call it maybe, I'm going to say b is going to go from 1 to cap b. So I had written down last time the for loop that's going to be iterating over these bootstrap iterations and getting these bootstrap replicates. That's the number of bootstrap replicates. You might be thinking, why don't we just enumerate all 2n minus 1 choose n? And it's just because it's too big. It's really big. We'd have to come up with some sort of data structure to check that we had every single one and cycle through it. So it's a computational chore. And you can come really close to that same idea just by throwing darts. That's controversial if we lived in the 1900s. So you've seen it done, you've done it yourself, you've played around with this, and if you don't believe me, go ahead and code up every enumeration and you'll notice that you're off in like the 13th decimal point if you crank up b really high. So a generic strategy is just make b really big and then just sample with replacement uniformly from the original sample. You'll get something really close if b is big enough. Usually cap b can be much smaller than the total number of unique bootstrap replicates. Don't make it too small. So I see all the time in seminars that people do some bootstrapping and somebody asks, how many bootstrap replicates? And they're like, 100. And it's like, oh, gotcha. That's what's wrong. Why is that? So make that thing big. And how did you check for convergence? Is B was big enough? You ran it for some big B, you doubled it, and you saw that you didn't change the answer. And so you just keep doing that. That might be a little bit too brute force, but you get the idea. So anything you want to report back, crank that number up bigger and make sure you keep getting the same number back. And if you're getting different numbers, B's not big enough. Okay, so all these bootstraps replicates, I'm just going to call them XB right here. These are just going to have resampled values right here. So I'm just going to call this XB1 all the way to XBN. So there's still n samples in here, and this is for the B bootstrap replicate. What do we do with all of this stuff? We just compute XR out of this by taking all of these S, B, I's. I goes from 1 to n, you divide by n. And I'm going to call this XR B. If we look at all of that, we just get back another mean estimator. So all we're doing is computing the mean. If I wanted to know at the end of the day, what is our best guess at X bar, or at the true mean, I'll just write the mean. What you might do is you might take all of these bootstrap samples, B, I'm going to go from B goes from 1 to cap B, and I'm going to divide by cap B. And this might be our new test statistic right here. I'll call this T bar right here for test stat. What we can see is these things right here are just means. So I'm taking means of means. And there's two different types of asymptotics that are going on. There's asymptotics in terms of B, cap B, and in terms of cap N. If I crank up B really large, B goes to infinity, can't actually do it, we're using a computer, but something really, really big, then we know that this number right here is just going to converge back to this number. And hopefully you can see that, because I'm just randomly sampling with the same frequencies that are presented in the original data set, and I'm averaging over those numbers. So if I crank this up really big, the numbers that appear here, these are all sums. So this is just a sum over a sum. We're going to be summing over the same frequency of numbers, and we're going to be normalizing everything properly. And so you can convince yourself that this number right here is converging to this as B goes bigger. And as N gets big, then this number converges to the true mean, what we might call mu. So two different types of asymptotics, all of that. I'll point out that the variance estimators are a little bit off from what you would expect to see from the IID replicate, because if I'm resampling that same point over and over again, then that point is correlated with itself in a previous sample. And it's that dependence that makes the bootstrap a little bit different than what's going on if you go out into the population and resample. So very similar stuff. So if N is big, that dependence falls off. So you can take this to a limit and think, what if I just sampled once? So and I only have one sample, and then I bootstrap over it. That's not going to work. So how correlated is that sample with all of the other samples that you get? Perfectly correlated. So in that sort of case, you're not really learning about the variability of the distribution, and you have too much dependence in your samples. If N gets big, the dependence falls off. Please.
Will the 2n minus 1 choose n number for just one data point? Wouldn't that just be 1?
Yeah.
And so
there's only one way to do it. Yeah, we probably didn't even need to do any math to convince ourselves of that. So there's only one, but N's just not big enough. But you're right, yeah, there's only one way to resample one point if there's only one point in the sample. So you're right. So that's just a sanity check that that number that we computed is correct. Anyway, the point is that there's two different types of asymptotics. N needs to be big enough so that you're representative of the original distribution. Okay, let's just finish up this example. One more thing before we do it. Let's just at least write down what a QQ plot is. I assume that most of you know but it's a way of comparing two different distributions. We're going to be using these a lot in simulation studies, and they're basically just confirmation that things are going right. So if I see the right QQ plot and everything is linear, I know you did the problem correctly. So QQ plots. Some people call these PP plots. That's how I learned it. I prefer to just call them QQ plots. So, but sometimes you'll see PP for probability and probability, and QQ stands for quantile quantile. I like quantiles because that is actually the probabilities that we're measuring. So it's a little bit more specific. So I might have two different distributions. So dist 1 might look like this. And dist 2 might look like this. I haven't put any scaling on this to tell you exactly what these are, so I'm just going to draw out the basic idea. So what I might do is I might chop this distribution into some number of quantiles. Let's just imagine I end up picking this to be the 05 quantile. So I'll call this Q 05, 0.05, and I'll call this Q for dist 1 right here. What that's going to be is that's going to be 5% of the area under this curve. So this would be 0.05 because the area under a density is 1. So I'm just going to measure that to be 0.05. This point right here is the 05 quantile for dist 1. I can do the exact same thing over here and pull out the point so that I have 5% over here. And I'm going to get a new quantile, and this is going to be Q05 for dist 2. And I'm going to just plot those next to each other. So I'll call this quantile for dist 2, and these will be my quantiles for dist 1. And I'm going to grab these 2 points, this one right here and this one right here, and I'm going to just plot them next to each other. And you can imagine what I'm going to do next. So I'm going to grab maybe the 10% quantile. So this would be the area to the left of that is going to be 10%. That's encapsulating all of that as well. And I'll call that the Q1.1 quantile. I'll do the same thing over here. So maybe this is the Q2.1 quantile, and I'm going to plot those right next to each other. And I'm going to just march through this and do this over and over again. The way that I'm kind of describing this is I would do this 20 times to get all of those quantiles. And I would plot those 20 points. And I would look at what they are. We know this isn't going to be super linear because we see that dip in the distribution. It's going to pull down one of the quantiles relative to the other. And so what we might be able to see, bless you, is that this distribution is relatively the same in some part of the distribution, and then there's a blip in here. And that might correspond to this. Everything is kind of unscaled here, so you have to use your imagination. You can do this for far more than just 20 points. You could chop this up as many times as you want. For data sets, you can do the exact same thing with the histograms. But for histograms, you're kind of limited on how many quantiles you can even look at. So if you're looking at an empirical distribution and you had 100 points, you could chop everything up into the 0.01 quantiles, 0.01, 0.02, 0.03. If you have 500 data points, you could look at the 1/500 quantiles. You could compare a histogram to a continuous distribution. You could compare 2 histograms to each other. So if you had 2 different data sets and they are both the same length, one thing you could do without even thinking about the quantiles is you could sort both data sets and just plot those sorted values next to each other. That would be equivalent. But if the 2 different data sets didn't have the same sizes, then you would have to probably restrict yourself to the coarser distribution, the coarser histogram. So there's lots of ways to do it. And what you're basically looking for is linearity. When you see linearity, you know that the distributions are the same up to location and scale. So if the distributions were exactly the same, the intercept would be 0 on that line and the slope would be 1. But if you change the location and the scale of the distribution, it'll just kind of tilt that line around. So if you do a linear transformation of your realizations, it'll still be a straight line. You can convince yourself of that. But I like to look at these plots so I can tell whether or not distributions are the same or if they're different. And I really like these plots because it tells me there might be sections where everything looks about the same. So maybe in the tail for a while it looks a little bit the same, and then there's some deviation in the distribution. So you get a little bit more than just are the distributions the same, yes or no. You get to see where they're about the same and how they deviate from each other. Let's come back to our simulated example. We'll use that idea to compare whether or not going back out into the population and resampling and just shuffling the data are approximately the same things. We talked before about n has to be pretty big for this to work, but it turns out that's what's going on. Okay, back to our Bootstrap code. Lights, no lights? What do you guys prefer? Nap out? So, at least dim lights. That's not bad. That's better. These lights are only a distraction. Okay. So this is our code from last time. We're getting a little bit of a 2-for-1 here because we get to see what an additive mixture model is. So I've kind of defined what that is. And I'm sampling from 3 different normal distributions depending on the coin flip. So I've got a 3-sided coin right here inducing these 3 modes. And the modes are really just normal distributions, and I'm laying them on top of each other. I'll have you sample from mixture distributions later in this class, and I'll be providing you some extra credit, but also when we do EM in this class, we'll be coming back to mixture models. So I'll have you estimate what the mixture components are later in this class, and we'll do some math to do that. Okay, so first part of everything is I'm just sampling from our mixture distribution. So with probability 1/2, I'm sampling from a random normal with mean 10 and variance 1. Probability 1/3, I'm sampling from a normal with mean -10. And with the remaining probability 1/6, I'm sampling from a normal with mean 3. I could have rescaled everything and changed the variance as well. I just didn't see the need to do that. Everything else in here is just bootstrapping. Bootstrapping is a really simple thing you can do, and it really just relies on being able to resample. So instead of reordering everything and looking at every permutation, I'm just every unique bootstrap replicate, I'm just throwing darts. Again, controversial idea. So it used to be if you said in the 1800s you couldn't do something systematic to beat something random, people thought there was something wrong. It took people at least 100 years to convince people doing things randomly is a really good idea. So you remove all kinds of bias. If you do it right, you can remove some variance in everything as well. So stratified random sampling might even be a better way to do this. But since everything is uniform, there's no real way to stratify everything. We're looking at the mean. So I'm just going to compute that every single time, and I'm going to compute it to what we're doing when we just go out into the population and resample over and over again. So let me just remind you, I'm looking at n is equal to 31 data points. The number of replicates I'm going to go out into the population recollector 100, and I'm going to bootstrap sample 1,000 times. There's no reason you need to make this number small. I should probably make it even bigger. So, but why not? Let's make it bigger. Good practice. So just throw another 0 in there. Back in the 60s, that might have freaked you out, but nowadays, get everything back just like that. Okay, bootstrap. That's going out into the population and resampling. That's kind of a cool one. And here's our bootstrap distribution. So we only had 31 data points to try to estimate this trimodal distribution. And we can kind of see from the QQ, I ended up just looking at these samples from here, binning up their quantiles, looking at their quantiles and plotting it against the quantiles here. You can already see that these things are a bit different. So question is that linear? Right there, I would say no way if I glanced at this. So what's wrong? You can see where everything is going wrong in this example, so that I'm not learning about the tails well enough. And so the tails on one of the distribution are heavier than the other distribution, and that's why they're both bending in that direction. So it seems to work okay, at least in the middle chunk. But I tend to think what happens in the tails is extremely important. That's usually what we should be focused on. So I'd say in this case we have, it kind of works, but not that great.
If you ran with a different seed, it would look different.
Yeah, probably, exactly. Let's just do that. This will reseed for me. So it did an automatic reseed on everything. So that one, it worked out pretty well. Same exact setup. So how do you know if it's going to work or not? The only thing you can really think about is, and it's pretty big, then you have some confidence that it might work. And so it can work, it might not always work, and you can't always know. And it just has to do with the representation of that sample. Again, sometimes in the random universe, things work, and sometimes they don't work. What we want it to do is to work on average. A lot of times it works. So in all these simulated examples, you should see periodic failures. So that's just what we're supposed to see. So error rates of 5%, things like that. There's no guarantees like that in this example. It really has to do with how wiggly the original distribution is, and if I have enough samples to figure everything out. Let's just run it one more time. And we notice that it kind of worked. It's a little off in that tail, not as bad in this other tail. So glancing at those two different distributions, I can't tell at all if they're the same. So that's just kind of a byproduct of getting things up and looking at histograms. So your eyeball is terrible at gauging if two histograms are similar to each other.
How are you deciding the number of bins?
I just used the default, so
Okay.
20. So yeah, exactly. I didn't put any thought into it. So 20. But again, this is just a visual tool. I'm not doing anything inferential with it. So it's possible that I could rebin this and they look a little bit more similar.
So the scales.
Scales are a little bit off, yeah, those. Let's crank up N a little bit. 31 seems a little light for all of this. So maybe make this 100, but 3100, it should work really well. But I'm getting more resolution as to what those distributions are. Still can't tell with the histograms, I'm just using default stuff. Yeah, it's really hard to tell. I'd probably want to yank this around. That's -2 right there, that's 0. This is 4, and that's like 5 right over here. How close are those distributions? They're not too far off from each other, but not exactly the same. Let's just check real quickly. If I look at this, I can grab that, just do one more figure. Figure 4. What I'm going to do is I'm just going to look at QQ plot of my bootstrap itself. What this does, if you just type in QQ plot and you just add one of these things, so I'm handing back my Bootstrap stuff, and I'm looking at the replication of coming out of the population, so I'm just taking those 2 histogram samples, punching it into QQ plot, and it will just chop everything up for me, so I don't even have to specify which quantiles. It's going to look at my smaller data set and use that as the giving me the quantiles to look at. If I do this without anything else in there and I just look at one of the vectors of, in this case, the Bootstrap's statistics, the vector of those that I get from Bootstrap replication, it's going to plot these against a normal distribution. So a normal 0, 1. That's what it does by default. Let's just run that one more time. Super.
There's an extra B.
Ah, yes, thank you. It doesn't even know what that is. One more time. That actually looks super linear to me. I'd say those distributions are pretty close. They're a little bit off. There's a little bit of wrinkles in there. One more time. If I look at figure 4 right here, where I'm just plotting everything, it ended up labeling everything on this plot. QQ plotted the sample data versus the standard normal, so it even knows to label that for you. This is super linear right here. So while I have some variability between these 2 different processes, if I ended up looking at the samples from the Bootstrap replicates, these ones right here, they look pretty normal to each other. And we know this because of the central limit theorem. So it's some sort of central limit theorem kicking in. This isn't exactly the central limit theorem because there's a little tiny bit of dependence depending on how big n is. So it's almost the central limit theorem. And we see that that's pretty linear. So we probably shouldn't be doing bootstrapping for learning about X bar because we could have just said it's probably about normally distributed. If you did do bootstrapping, you would get about the same answer. So it doesn't really hurt you. You just went through a lot of computation because you didn't know any theory. Okay, here's where the bootstrap might be a little bit more applicable. If all of a sudden I want to look at some really weird test statistic, I'm not going to use a strange test statistic, but I can change this to maybe the variance or something, and maybe we don't know what the distribution of variance is. I have to change this in 2 places in my code. And going back out into the population and the bootstrapping step. Does anybody know what the distribution of variance is? Any ideas?
Chi-squared, if there's no...
Yeah, it probably has something to do with a chi-squared distribution. It's not scaled right to be the standard chi-squared. So it's a non-central, but it has something to do with a chi-squared. If I came up with something different that I just wanted to look at, I might not know the asymptotic distribution of that, and maybe nobody knows. Let's run this one more time. Bootstrap example. We see figure 4, that's not normally distributed right here. So turns out if I plotted it against some type of a chi-squared distribution, it would be linear. Here's how well going back out into the population compares to bootstrapping. They're not that different, but there's a little bit of off behavior over in this tail right here, but they're not inflecting down. So it's roughly linear. So not too bad of a job. Can't tell with the 2 different histograms what's going on, but we can see that bootstrapping is maybe well approximating what happens if you go out into the population. I have this code on the website, so feel free to download it, play with the toggles, see what the limitations of all this is. I think it's a reasonably okay idea. Kind of like the idea. Keep in mind, everything has to be IID to do what we've done, so there's a major limitation on things. Any questions about all that? Later on, I'm going to have you code this up and compare some methods to each other so we get a feel for how things work and we're not just going, oh, asymptotically, as n goes off to infinity, this works perfectly, because that's not realistic. That's just an idea, a concept. So I'll be having you code this up and you can lift from my code if you'd like, if that helps you out. I'd like to switch gears into order statistics. Has anybody read through that section of the book yet? Probably a really good idea just to skim it. There's a bunch of formulas, right? And the question is can you memorize all those formulas? What do you think, Colby? Yeah. I kind of remember this when I was in grad school going, how am I going to memorize all these formulas, all these big sums and things like that? I'm going to teach you to think about it conceptually so that you can always rederive that formula from a picture. I want to start with an example. Let me just start with an example. This isn't in the book. I'm going to take a day or two to motivate all of this and get through it all. And then we'll come back to those formulas they've derived for you in the book. Joint order statistics, that formula looks a little bit more heinous. I'll have you draw the correct formula or draw the correct picture so you can never forget how to do this. You can also extend it to joint distributions of 3 or more order statistics. Just kick things off with an example. Start with a question. So say I've got some distribution, xi is going to come from some density function. And I want to give us a concrete example to start out with. So I'm going to say this is x over 2, where x is going to go between 0 and 2. We can check in a second. I know what Dylan's doing. He's integrating in his head, making sure this integrates to 1. How do we do? So you can see it already, right? So, okay, this is a distribution right here. X lives between 0 and 2. Somebody help me out. What distribution is this? So not even a contender. Check the bounds first, where it lives. Anybody recognize this distribution? Oh, good for you. Every year for 10 years, people say uniform. It's not uniform. So if the CDF, if it looked like that, if it were linear, that's uniform. Who knows what this is? So it just looks like this. That's the distribution. So it just says I'm getting more and more samples as I get closer to 2. I'm putting more weight over there. In my code, I showed how to sample from this distribution. And it turns out you can do this analytically, and I can set up a perfect sampler to grab samples from this distribution. It's the inverse CDF sampler. I think next time when we come back, I'll tell you what inverse CDF sampling is, just to slide another concept in. So it turns out it's the answer to all of these little how do you sample from this distribution for the first homework that's going to be due on Friday. We'll do a review session on Thursday. And I made myself a note to post the Slack page sometime today. So by Wednesday, you'll have the Slack page, then we can communicate over it and figure out what we need help on for the Thursday review session. So that's all done. Okay, this is just some distribution. I just made it up because it's easy to work with. Let me just ask this question. So let's just define xi is the ith largest sample. I'm going to say I'm going to sample from this some number of times. I is going to go from 1 to n. And let's just give n an actual numeric value, 6. So I've got all my xi's right here. Maybe that's my first sample, maybe that's my second sample, maybe that's my third, fourth, fifth, sixth. So I've got these samples, and they didn't come ordered, they came unordered. But then I can order them at the end of the day. I might call this x1, this would be x5, and this would be x6. So I'm going to draw the midpoint right there. That's 1. Put a sample in there. So I'm going to let that be 1, just that point right there. Let me just ask a question. What's the probability x5, this is the 5th largest thing. Bless you. I'm going to ask this question. What's the probability that x5 is less than or equal to 1? So I'll put this in a probability statement. What do you think? Is that big or small? I don't expect you to compute the number and to tell me what it is. That would be amazing. It's probably pretty small. Just by looking at the picture right here, we expect for numbers to get stacked up over here. This doesn't even look right. I probably should have more numbers over here. It's just a random sample. So you never really know. But if I got more and more numbers, I'd expect everything to be slammed to the right. So this is probably small. Let's distinguish this. If I just ask the question, what's the probability that any old xi, and I'm not putting a brace on it, so I'm just calling it just some IID realization, just ask the question, what's the probability that that's less than 1? This is a relatively easy question. So this is just going to be x over 2 between 0 and 1 dx. So that's going to be x squared over 2, and I'm going to evaluate that between 0 and 1. 2 times 2. Up my exponent by 1, divide by my new exponent. So that's just x squared over 4. That's 1/4. So that probability is, I wouldn't call that a small probability, it's moderate. So let me just ask a slightly different question. Do you expect this number to be bigger or smaller than that number? Smaller. Good intuition. So probably getting smaller than that. I just want to distinguish the probability that any xi less than 1 is a very different question than the 5th largest thing being less than 1. So, and there's dependence between all of these samples. So order statistics have dependence with each other because I have to order everything relative to each other. So this is our first not IID sort of question. It comes from an IID model. The original samples are IID, but once I shuffle and order everything, I've created a dependence in everything. So we have to account for dependence when we're answering this question. I wrote a simulator to do this. I want to see if we can build this up analytically, but I think just conceptually, I always like to see if I can just invoke a process to estimate something. So this would be called a Monte Carlo simulation. Just real quickly, what is Monte Carlo? It's casino. Yeah, exactly. Where's Monte Carlo at? Monte. That is where it derives its name. Everybody see that? Okay, so I have some sampler. I'm going to crank this thing up really high. Let's not do anything too crazy right here. Monte Carlo is where I just do a random experiment. And I average over that random experiment to see what the average behavior of something is. Monte Carlo is set up formally as an algorithm. It gives you a random answer in a fixed amount of time. And that answer converges to the truth if I let that thing run longer and longer. So there are other algorithms where I can specify the tolerance on things, and then the waiting time that you have to wait to hit that tolerance is random. And humans don't like that. So if you've ever sat in the car waiting for your mom while she's in the grocery store or something like that, it is a painful exercise because you don't know how long you're going to wait. So, but if you knew exactly how long you were going to wait, it's not that irritating. So random running time algorithms are called Las Vegas algorithms. And so just to build off of that metaphor. So fixed running time algorithms where I fix n in advance and I do it some number of times and I get a random answer back, that's called Monte Carlo. This is a sampler right here where I'm going to draw from this density function. So same distribution that we were looking at before. I'll explain this later on. So for every uniform that I draw, I can re-get a sample from this distribution. I'll try to explain this later. This is called inverse CDF sampling. So if you've ever taken a probability class, which you all have, there's a chance you already know what this is. Let me just ask real quick. How many people know what inverse CDF sampling is? How many people do not know? Okay, plenty of people. I'll point this out. The proof that I'm going to show you that inverse CDF sampling works is exactly the same proof that we will come up with in chapter 8 to show that p-values are uniformly distributed if the null hypothesis is correct. So the math is entirely the same. It's just a neat little engineering application of that theory. Okay. You don't need to think about one to do the other. They don't have much to do with each other. It just turns out the math is exactly the same. Okay, so I'm going to be sampling some number of times replicates. My replicates is going to be how many times I want to repeat this experiment. The number of samples I'm going to grab is going to be an input in my function. That's n. In our case, that's going to be 6. And then I'm going to look for the jth order statistic. I guess I called it I on the board. So hopefully we're flexible enough to do that. And I call j 5. So I just resample over and over and over again. Every time I sample from this line right here, I grab a sample of n samples, in our case 6. So I'm not doing it over and over again to sample, I just do it all at once. Then I sort everything, and then I grab the jth largest thing. And I just grab all of those, I hold them, and then I'm going to check to see how many of those things is less than or equal to 1. That's all we're doing right here. So I'm just summing over the number of them that are less than 1. So I'm looking at their empirical frequencies of how many times I collect from 6 objects. The 5th largest thing is less than 1. So, and then I just normalize everything and I report back that answer. So order stat gen. I've already got my numbers plugged in. 6 and 5. N is 6. J is 5. I run it. There's my distribution itself. So this is the distribution of x5 itself. So I've got some distribution, and I can look at this number. 0.052. So it's relatively small. Let's crank that number up a little bit. Rerun this again. 0.043. So we notice those two numbers changed a little bit. Let me just rerun it again, 0.0047. So they're starting to converge. If I put one more 0 in there, this thing might hone in on that exact number. Not exactly, but close enough. It takes a little bit longer to run, 0.0046. I'll run it again, 0.0045. So I might want to crank that thing up a little bit more, but I have an idea that it's around 0.004. So I'm a little bit imprecise in this next decimal place. But I know this number is tiny. So if I want to really hone in on what this number is, either I can learn some math or I can keep adding zeros here. Let's see if we can do this mathematically. Compel you to think there's 2 things that can happen that make x5 less than 1. So when I say x5, I mean the braces, the 5th largest thing. So there's 2 scenarios. So either x5, I'm going to say this, I'm going to say scenario 1 is 5. Instead of saying samples or replicates or instances, I'm going to change the word to things. So just for this example. So I'm going to say 5 things, but they're samples. The 1 is just coming from here. It's just an arbitrary number. I could have changed that to anything between 0 and 2. So 5 things less than 1, or scenario 2. 6 things. If either of these two things happens, I know that the fifth thing, the fifth largest thing, is less than 1. If I say there's only 4 things less than 1, I don't know how big that fifth thing is if it were less than 1. So there's no guarantee if I end up saying only 4 things are less than 1, whether or not that fifth thing is going to be bigger than 1. But these are 2 guarantees that if 6 things are bigger than 1 because of the ordering of everything, or 5 things are less than 1, those 2 scenarios contribute to this right here. So I'm just going to redefine a random variable. I'm going to say let z, I think this is the variable that they use in the book, is equal to the number of things, these are just the xi's, that are less than 1. So I can take this continuous problem, and by the redefinition of this random variable, I can turn it into a discrete probability problem. So because there's just these discrete cases that contribute to this total probability. So this question right here is exactly the same as the probability that z is equal to 5, or z is less than 6. Z is equal to 6. So 6 things are less than 1. I can just draw this picture right here. I've got 5 things right here. And I've got 1 thing over here. So in this scenario, I'm saying exactly 5 things are less than 1. And this is exactly 6 things are less than 1. I've got this 1 right here, 5, 6. So this is 6 things. One thing I want to compel you to think about is I don't care which order those came in. It doesn't matter. So if this was the first draw or that was the first draw. So there's lots of different ways that I can have this scenario arise. There's lots of different ways that I can have that scenario arise. And we have to account for all those different scenarios. So this is really just a combinatorial problem. So, and it's really just a binomial problem. Let's just compute this probability. And just ask the question, what's this area under this curve? One-fourth. Came from this right here. So that's the probability that any one of the xi's could be less than 1. So I want to just first account for this. Probability that z is equal to 5. This can happen in lots of different ways. So what I want is I want 5 things over to the left of 1, and I want 1 thing to the right of 1 for this scenario to be true. And again, there's lots of different ways that I could have had these 5 samples appear in those places. I don't really care about the order in which they appear there. I just care that they're to the left. So how many ways can I have that happen? It's 6 choose 5 different ways that I can rearrange all of these and get exactly the same thing. So this is 6 choose 5 things are to the left of 1. They happen with probability 1/4. There's 5 of them. They were to the left of 1. And then I have 1 minus 1/4, and that's my 1 thing to the right of 1. Right here, that happened with probability 3/4. So apologies for my scaling, that's 3/4 right here. I know it doesn't look like it. So we can do the exact same thing and look at the probability that z is equal to 6. This is a little bit easier to account for, but we'll just write down all of the placeholders in this probability. How many different ways can I rearrange all of these things And it's the same thing, that's 6, choose 6. So there's really only one way that I can think about it. I'm going to have 1/4, all of them are to the left of 1, and 0 of them are to the right of 1. And I just add these two things together. This will give me that number, 0.004 or so. So that's the probability. We're going to come back next time and we're going to write this out algebraically and reintroduce that instead of just dealing with the number 1, we can turn that into a variable and look at how we've done this. So if I want to answer this question right here, then I just need to change these numbers that are going in here. What would I do? I would end up looking at 6, choose 5, f of x raised to the 5, 1 minus f of x raised to the 1, plus 6, choose 6, f of x raised to the 6, 1 minus f of x raised to the 0. And so in general, this would be that probability. So again, all we're doing is we're just counting the number of ways, scenarios that I could have that 5 things are less than x, or 6 things are less than x. Next thing I'm going to ask you after we write this down is what's the density function for this? And we all know the answer. I need to take a derivative of this. What I want you to see is when you take this derivative over this thing, there's a lot of cancellation that happens. And it's not a coincidence. So I'm going to remind us about this problem next time when we come in. We'll write down this. And then I'm going to start taking derivatives, and we're going to produce the density function for x5, the 5th largest thing. And that's what I actually plotted in that histogram that I erased real quickly. So we'll come back, look at that, see what that density function looks like, make sure we can write it mathematically, and we're going to derive a very general formula through all of this. So we'll come back next time, do that, and then I'm going to take you through joint order statistics. And that'll be kind of the basis for coming up with the probability distribution of the range and the mid-range, that example that's presented in the book. We need to understand transformation of variables of order statistics to build that up. So that's what we'll do next after that. So if you're looking at the book as to where we're going, order statistics, joint order statistics, and then we'll be jumping into that example on the range and the mid-range. Thanks, you guys. I will see you on Wednesday. Keep your eyes posted for an invite link to the Slack page. You should be getting that. If you don't get it on Wednesday, I'll ask you to come up and see me and we'll match you.